This is TAU Unbound, the English language podcast of Tel Aviv University. Please welcome your host, Ido Aharoni, Tel Aviv University's graduate, member of the Board of Governors, lecturer, writer, and veteran diplomat.
Welcome to yet another episode of TAU Unbound. I'm Ido Aharoni, your host, and today it is my pleasure to host Professor Hagit Messer-Yaron, who is a very distinguished member of the Israeli academia. Let me just tell you a little bit. Now she's Professor Emerita in the School of Electrical Engineering at Tel Aviv University, but she held many important positions. She received her Ph.D. in Electrical Engineering from Tel Aviv University, and after a post-doctoral fellowship at Yale University, she joined the Faculty of Engineering right here at Tel Aviv University in 1986. This is around the time I was studying here. Over the years, she has held leading positions, including, listen to that, Chief Scientist at the Ministry of Science, the Vice President for Research at Tel Aviv U, which is a position that holds a lot of weight in this university. She was also the president of the Open University. The Open University in Israel, those of you who don't know, in absolute numbers is the largest university in the country because it has more students than any other university. It's not the largest campus, but has more students than any other university. And she was also the vice chair of the Council of Higher Education and the co-founder of a startup company called ClimaCell in 2016. Wow. What an accomplished career.
So I don't need to speak because you took all the time to go over my CV. Okay.
So today I'd like to talk to you about two things. The first is electrical engineering, and the second is the state of academia, which is, I think, something that is on people's minds after 10/7, especially when they're seeing what's happening in the Western world. But let's talk about what happened to universities in general since World War II. But let's begin, as we always do, with your own personal background. Tell us about yourself. How did you become an electrical engineer? How did you become a professor?
Thank you. I like this question because going back many years ago to the cases where you need to take personal decision bring good memories to me. Because I was always what we call broadband in the topics that I was interested in. I was interested in art and in literature and so on. And then the first decision should have been to go to study either science or humanities, art, etc. And then I made a rational decision saying, okay, if you do science, you can still be interested in art, science, in literature, etc. But the other way around is much harder. So let's pick up the better way. Then when I decided to go on science, again, it was an open question, what kind of science? And it's hard decision. Till now, people come to ask for my advices. Because you can either go to experimental sciences or to mathematics or to whatever. But from a very early beginning, I realized that the most important for me is, as a generic tool, is to look at systems. Almost anything you can model as a system with input, output, processes, etc. And then I looked, where do you study about systems? And it happened to be electrical engineering. So that's why I, at the end of the day, moved into electrical engineering. And I must say,
this happens when you realize that you're interested in the study of systems, in that case, electricity. This happens when? High school?
No. After the army, actually.
After the army.
But again, it's not the electrical systems. In electrical engineering, you characterize systems whatever they are. And this is wonderful because it can be applied to any kind of system.
So tell us a little bit more about what is the actual meaning of electrical engineering?
So it's a good question. I used to ask my students in the second or third years, do you now know what electrical engineering is? It's a generic name under which you have many different non-orthogonal, non-overlapping topics. So within electrical engineering, there are different directions. Some are more physics-oriented, some are more mathematics-oriented. But at the end of the day, from my point of view, what characterizes electrical engineering is the concept of a system. Whatever you look at, either a physical system or man-made, human-made technical systems, computer or whatever, you can characterize as a system. You put in input that you can either control or not control. You desire to have some specific output, and then you can design or you can study the system in between. And I must say, as I said at the beginning, when I moved into electrical engineering and I decided to study it, my view was to use this tool for biological systems. Now it's a common knowledge. I'm talking about many, many years ago. But also you can characterize biological systems as a system. And then if you have the generic tools, how to deal this system, maybe you can see things that otherwise it is harder to see.
So give us a couple of practical applications of electrical engineering so that people can relate to.
Classically, within electrical engineering, you study either control systems or communication systems or computers, which is kind of a system, hardware and software. You study the physics of system, wave propagation, you study about devices, etc., etc. I think in our program in electrical engineering, we have 7 or 8 different expertise channels that a student can study depending on what he or she like best. But
And you find that electrical systems behave much like systems in biology, in nature?
So again, when you talk about electrical systems, if you think about voltage and other characteristics of electrical systems, this is just symbolic. Actually, our students in the first or second year, they already know that in any system you have 2 variables which are equivalent to voltage and current, but you have it in any system, in mechanical system, in biological system. This is the model that I'm talking about, which can be applied to various kinds of systems. And this is wonderful because once you look at it as a concept, then you can see things that it is harder to see if you just describe what you see. I very much believe, and I think that modeling is a great tool prior to analysis, and then you can learn from it. I'll give you just one example, which is
Please.
kind of introduction to what you're going to ask me about my specific research now. When you're looking at biology, then you know that the core of everything now is the DNA, which consists of a sequence of nucleoid which are kind of a code. Okay, you have 4 letters in this code, and this is the source of all our everything, of our biology, of our characteristic of everything. Now, within electrical engineering, there is a big field of coding. Can you relate the two? Look, for example, on error corrections. In engineering, you do a lot about error correction to make sure that the signal that go from your cellular phone or from your computer to a different place, even in the presence of noise, etc., can be rightly transferred and corrected. And also in the DNA, there are many problems with these letters. And the question is, can you relate the error correcting that the human body or life do? Can you relate it to the system that we have, that we know in technology? This is still an open question. I looked at it many years ago, and I think these are the kind of most interesting problems in science, the way I see it.
Now, if there is an error in the interaction between the parts of the DNA, and we're able to fix those errors the same way we fix any signal in, let's say, in a cellular system, then the applications are just beyond imagination for the health of humans and so on.
You're right, but luckily in the academia, we don't need to think about applications. We are curiosity-driven. For me, it is more important to model, to understand, to see, and then the application come after. but we can start by understanding what is there. For example, I'll give you a kind of a philosophical aspect of this question. You know that the evolution is based on mutation. Now I'm talking not about electrical engineering, about a different topic, but mutation they are happening because of a fault in the DNA, because of errors in the DNA, right? Now, if you have a perfect DNA repair process, then you kill the evolution. Is it good or bad? So in technology, the optimization criterion is usually to have zero errors. You don't get to it, but at least that's what you aim at. I'm not sure that the biological process really aim into zero errors.
So the mutation is part of the natural design.
Yeah. So philosophically, it is a little bit different, and it makes you think. Maybe it's also good in technology.
Right.
Not
but
only
mutation also causes cancer and other things. So there are two sides to that. So it's a beautiful segue to something I read about. I went to your website, which I urge all our viewers and listeners to visit, a beautiful website that lists all your accomplishments, but also talks about your current work, which is fascinating. And so Professor Hagit is involved with the Cellular Environmental Monitoring Research Lab at Tel Aviv University, and they have even a nickname. It's called the Cell and Mon. Cell and Mon focuses on research in the areas of opportunistic sensing of the environment using advanced signal processing tools. Now, that's a heavy sentence that you have to break down for us.
If I don't succeed, I have a student here. He can help us. Actually, it's not so complicated. My original field is called signal processing. And signal processing is a well-established field in electrical engineering, where you actually process signal to extract information related to different phenomena. Like, for example, for many years, we used to analyze signals from sources like radiating sources to establish their location, their direction of arrival, etc., passively. So the signal is not not transmitted for you to know where they are, but you can receive it, analyze it, and then get information about where the signal is. So there are many applications of signal processing. In many years it was mostly in military, but not only. Military applications and others, as I said, well-established field. Now, the idea of extracting information from different signals and sources can be all over. And the field that you just mentioned now is related to something that I believe that we are all familiar with, especially people my age or maybe your age. Before, when we had broadcast television, before cables, etc., and it was rainy, you used to see on the screen that the signal is some way white and so on, because electromagnetic signals naturally are influenced by weather. They use the atmosphere as a propagation channel, and they are sensitive to changes in the atmosphere. So this is a well-established and known phenomena from the time of Maxwell that study wave propagation. What happened like 20 years ago, maybe more, when the cellular technology evolved, that the digital technology used to keep all the measurements that before were there. Nobody cared about keeping them. But for example, in cellular companies, they used to keep information about the signal level to see if there are problems in the network, okay? So my idea back in 2004 or 2005 was to get this data, these measurements, existing measurements, from cellular companies, and to analyze them using signal processing algorithms to monitor environmental phenomena, more specifically rain.
Rain.
Yeah, mostly. Because these signals are very much sensitive to rain. Now, once you start thinking opportunistically, you get many opportunities. because the conventional way to monitor weather is by designated equipment, like radar or satellite or rain gauges, either electronic or the conventional rain gauges, which are like this, okay? But there are not too many of them. Like, for example, in Israel, you have not more than 500 local measurements, rain gauges. But if you look at cellular links, cellular connection that connect the base station, you have like 10,000. So when you have more data, you have more accurate measurements, you can really map the rain, for example, in a high resolution, tempospatial resolution. And if you have better idea about what's going on, then you can also use it for many applications.
So when you use the word opportunistic in the context of your work, just opportunities that along the way, things that you can apply the same methodology. So you said we can measure rain, but we can also measure traffic.
Actually, it's interesting because once we published this idea in a short paper in Science magazine back in 2006, the first company to approach us was a company which dealt with traffic. And they say if we have better monitoring of weather, then we can better control the traffic because we know when there are going to be problems with the traffic. The use of accurate monitoring of weather, as I said, it has many applications. You can use it for insurance to see what happened in agriculture, if there were flooded in a specific field. You can use it for city planning, like different things within city that are related to even when and how much you need to water the garden. This is also an application that can save money. Most important, for example, when we analyze the existing measurements in the Negev, we prove that the terrible disaster that we have in Nachal Tzafit 4 or 5 years ago, where 10 young people lost their life, we could give a very accurate alarm 40 minutes before. Because there were indications there, exactly local indications through the level of the signal in the backhaul of the cellular system that indicate the amount of rain, and if you calculate it, you could be sure that it is going to be flooded. So there are many applications, and the idea is you don't need to build more equipment, but if you use measurements and data.
Yeah, I like the word opportunistic in the description because it's an unusual application of that word.
I must say, when we started to use it, some English speakers, which I'm not, say it has some negative.
Right.
Right, but and then we say, okay, maybe we call it virtual gauges, etc., etc. But then we found out that opportunistic is a good description. And now there is, for example, in a European network, the European Committee put money on a network which is called OpenSense, Opportunistic Sensing of Weather. And we have more than 130 members from more than 30 European countries that are dealing with it. So opportunistic became a more popular term now.
Yes. And so tell us about the work of your lab. And I know that you have a colleague here with you in the studio. Tell us about the future in terms of what are your plans for the lab?
It's a good question because this is example of, in a way, interdisciplinary or multidisciplinary research, which in one hand it has many opportunities, but on the other hand it is challenging. For example, right from the beginning, we work in close collaboration with a professor from environmental sciences, Professor Pinchas Alpert, who is a meteorologist, and we definitely need his expertise to understand what we see on the signals, right? But then the application of these technologies come together with challenges. Because you need to speak with communication companies to get the measurements, And the application is in very different fields, in meteorology, hydrology, and others, and they don't speak the same language. So unfortunately, in a way, we found out after almost 20 years that to get products, which are public good products, based on this technology is challenging. Luckily, there are a non-profit organization like the World Bank and the European Commission and so on that realize that this technology has high importance for developing areas like in Africa, in other places where actually designated equipment for monitoring weather almost doesn't exist. So they put money in projects that use this technology in developing countries. In the developed countries, money is cheap. I'm sorry to be cynical, but sometimes it is easier to raise more money for designated equipment than to try to gap the bridge between the communication community and the meteorological community. So I'm not sure about the practical implication. There are several meteorological centers like in the Netherlands and in Sweden that are interested in implementing our technology in their everyday life. But it's in a way limited. The potential is there. And what we do in academia, we prove the potential that through papers, through many other academic work that we do, but the application is the next step, and we hope that it will happen, and we are part of organizations that are working on it. What even more interesting, and my student Dror, who is here, is very much involved with it, there is a new concept now in signal processing which is called ISAC. ISAC stands for Integrated Sensing and Communication. And when they talk about the next generation of cellular communication, the major change with the next generation is that the system will not be only for communication, it will be also for sensing. It will be all integrated in the technology. Now, when we look at what we are doing, we are already doing ISAC because we use the communication for sensing. And what Dror and other project in our lab is doing, looking at the other way around. You can also use the sensing capabilities of the network for improving the communication. I give you one example. When it is rainy, the signal is faded. Okay? This is, as I said, the fact that came from physics. Now, if the signal is faded, usually the conventional networks are reactive, meaning that when the signal is faded, then they transmit more power, or they change the modulation, or they do whatever is needed. Sometimes it's sufficient, sometimes it's not. But when you talk about future technology like autonomous cars, you cannot afford to be reactive. Because if you lose communication, even for a very short time, you may cause an accident. What we are doing, and again, this is part of Dror's research, and we have a project with the Columbia University, we are doing the other way around, meaning that first, due to sensing the weather, we know that it is going to be fading, and then you can, in advance, make sure that the quality of service of the system is sufficient. So this is the way that we look at it now, not only as sensing of weather, but as integrated sensing and communication. So this is one direction of the lab. And the other one, which I like very much, but it is more anecdotal, is bird watching. Actually, all our research is based on the fact that when you have a beam between transmitter and receiver, then this beam, when it is raining, then you have the drops and it changes the signal. But if you have a flock also going through this beam, you also detect some changing in the signal. And we had a very interesting paper showing that you can use this opportunistic approach also to monitor bird migration.
And soon you will also be able to monitor drone activity.
Yeah, absolutely. This is another challenge. Again, it depends, because we are talking opportunistically, then it depends on the sensitivity of the signal. If it is only a single drone, maybe it won't be sensitive enough for it. That's why I was talking about flocks.
Right.
But what I claim, and it is very much related to the new, to the modern wave of artificial intelligence or data-driven research, once you start to look at available measurements and resources and you think about extracting information from it, then it's unlimited. You can do many, many things which are done by commercial companies like Google, Amazon, etc. But we are talking about the physical environment, and it's extremely interesting what you can get out of it.
Now, let me shift to an entirely different area, because you are also wearing the hat of serving as an executive in Israeli academia. You were the president of a university in Israel. I mentioned that. You were vice president in charge of research. You have a perspective that very few people have. Now, we, especially post 10/7, really some things came to the surface. For example, the big question about the relationship between education and learning. If we invest in education, does it mean that we improve the process of learning? I think that what's happening in American academia these days, where you see less and less emphasis on learning, more and more emphasis on social engineering, is disturbing to a lot of our viewers and our listeners. And I'm just curious about your perspective. You know Israeli academia very well. You spent time at Yale. You know American academia very well. How do you read all this thing that we see, all those, the willingness of apparently educated people to side with a barbaric pre-civilizational organization like Hamas?
Let me start with a different point of view. When we talk about academia, I think we at least in Tel Aviv University and in other what we call research university, we are talking about two main components, the research and the education or learning, meaning the students,
the teaching.
Yeah. And once it was all gathered together, I mean, both research, teaching, and the certificate saying that you are academician, that you are qualified, came from university. In the reality nowadays, this is no longer the case. Okay, even research, people, and you see it with students. Sometimes I'm amazed. They don't really believe that there are questions that you don't have answer for. They believe that if you look hard enough, you find the answer because somebody else did it. But research is based on the idea that there are open questions and you need to do research to find the answer. But they are not trained they became from researchers, they became searchers, So now they search for answers instead of research for them. So research brings in many challenges to academia now, both because people are less practiced in looking for solutions because solutions are so accessible everywhere, but also because what we mentioned before, that even academic research became more and more dependent on third parties' data. Before, in academic research, all you needed were resources. If you have enough money, you can design your experiment, you can do whatever you want, and then you can make your research and come out with new knowledge. Now, many of the modern research, which is data-driven, depend on third-party data. As our example, we depend very much on data from the cellular companies. Luckily in Israel, and this is maybe the right place to acknowledge the companies in Israel which collaborate with us pro bono, just for the sake of research, all the companies, Cellcom, Pelephone, and other smaller companies, they provide us with measurements. But this is a challenge, especially if you want to have access to measurements which are of value to the company. For us, this is not the problem. So this is a big challenge for academic research. And you ask mainly about teaching, but I talked about research because from my point of view, students come and go, but university is first of all the faculty and the research and what we do there. Now, with respect to students, this is a big question, and I'm not sure if I'm an expert on this because, as you said, the environment has changed, and many students feel, or many young people feel that they don't need university to get the knowledge that they need, and sometimes you don't even need the certificate that the university gives you. But more than it, there is a question that I'm not sure about the answer. Are students part of the academic community, or are they kind of clients or customers? It seems like a technical question, but from my point of view, it is more deeper than a technical question.
Yeah. So are they customers of the system, or they're participants in the system?
Or they are part of the community, yeah.
Yeah.
Because if you look at the time frame, most of the students, they spend here 3, 4, 5 years, and then they have their life. So they are more like customers. But in many cases, especially if you look in Israel at the political arena, they play the role of part of the system, of part of the community. For example, if you look at the legislation, there are two main laws for higher education in Israel. The law of the Council for Higher Education from 1958, and then there is another law, which is much younger, for the students' right. And if you compare them, in many cases, they even contradict. Because the students' rights, when you talk about rights, then you look at it, it is more related to the political regime. And during the last unfortunate period since October 7, you could see it in the Knesset, in things that they wanted to have through legislation, some specific approach to students serving the army, etc., which should have been, from my point of view, solved within the institution. And I think that the institution like Tel Aviv University did a great job coming and helping the students who were connected to this. But once and the students in Israel, they are important population, good population, and they have political influence on the system, then in a way it skews the mission of higher education. So it's a big question. In the US, it's a different political regime, so I am not sure it is comparable.
I have a feeling it's not.
Yeah.
Mostly because...
When I say I'm not sure, I mean...
Yeah, I have a feeling it's not, mostly because, I also teach in the United States, and I think that Israeli kids, and I don't say that, in any way that, to undermine or belittle American kids, but I think Israeli kids are more resilient because of their life experience and the military service.
And they're older.
And they're older.
They're much older.
Yeah.
I mean, there is a big difference when you talk about 18s, 19, 20 years old.
I was in Denver in November of 2023, a month after the war broke out. And I faced a very vocal demonstration as I came to speak in this conference, a Jewish conference. And I could see the anxiety on their faces. So they were not demonstrating out of self-confidence or knowledge or conviction. They were, it was almost a cry for help in many ways. They were anxious, fearful. They were all wearing masks. These are all students, young 18, 19-year-old, 20-year-old students in Denver. And I remember asking them to take off their masks.
And they didn't?
They didn't, but they were afraid. And, that shows me that there's no resilience there. But in any event, listen, it was such a treat to spend this time with you in the studio. Professor Hagit Messer-Yaron, thank you so much
Thank you.
for your generosity of time and sharing your knowledge.
Thank you.
We'd like to wish you good luck in the incredible work that you do, and hopefully we'll get a chance to host you again.
Thank you, and thank you to the people there.
Yeah,
that
in
back
the
you up.
control, we have a whole team in the control room, and I'd like to say goodbye to our listeners and viewers from Tel Aviv until our next episode.